So, welcome to Lecture 35. This is going to be on purposeful design. Just a couple announcements before we start. So homework 11, all right, I'm saying it's online. It's not yet online, but it will be very soon. That's going to be due in 2 weeks on Friday, December 4th. Lab number 5 is due today at 5 p.m. Pacific time. I guess Naomi asks on the chat, where is everyone? This may be what the reason is right now, that lab number 5 is done, it is due. And so there may be people scrambling to finish it. I don't know what the reason is, but yeah. You've noticed it's a very popular lecture today. But anyway, lab number 5 is due today, and you have lab number 6 already online and due Friday, 12/11. So that's December 11th. That's the last day of RRR week. And you see how we've done this. Your homework number 11 is due 1 week, and then the next week your lab is due. So we don't have homework and lab due in the same week here. And this homework 11 is actually going to be your last homework. So you won't get another homework after that. Next week is a non-instructional day, Wednesday. Next week, Wednesday, is a non-instructional day. So we'll only have lecture on Monday next week. And that crimps things a bit, which is why I'm changing a bit the lecture topic sequence here. After finishing this multi-transistor example, where we're doing the high frequency part right now, we're about to finish that up. I was going to go into MOS inspection analysis, but instead of doing that, what I'm going to do is go into purposeful design, which is going to be more helpful for your lab number 6. And so I just want to do that earlier, so that over the weekend, over the next week, you'll have everything you need to be able to do lab number 6. And so more announcements. I have computed your z-scores. So you've probably all noticed that you have your lab scores and everything is up to date as far as lab scores. I guess the homeworks, we still have to update to some degree there. But I will start sending you your z-scores individually. I'm just going to give you the value of your z-score. And I won't say anything about what it means and that sort of thing in the email, because I've got many emails to send there. But I will just give the value, and then we'll discuss what that means in lecture, in a future lecture. Okay? So with that, any questions about any logistics in the class? Okay, seeing none. This is the example we've been working on, and we did the midband analysis. We did the high frequency. We did a lot of the high frequency analysis. And this is part of that high frequency analysis that we've done. So this is the small signal circuit that you need for high frequency analysis. You can see all the capacitors in there. You see that we eliminated this capacitor. We turned this capacitor into Miller capacitors. And then we did the analysis necessary to compute the high frequency cutoff, which is 1 over the sum of a number of time constants that have to do with if you're looking at a node, then all of the capacitance from that node to ground, and all of the driving point resistance from that node to ground, which is R2, same thing for node 3 and node 4. But then when you have capacitors in feedback, after we turn C mu into Miller capacitors, it's now just the C pi 1 and C pi 2. So the two C pi's. These are things that we actually did a small signal analysis using the hybrid pi model last time. To determine their driving point resistance, and we ended up with this equation right here. So an R pi naught is equal to whatever the R pi is for that transistor in question, in parallel with the resistor seen looking out this way and looking down out the emitter, divided by 1 plus GMRE. And we also determined the time constants associated with each of these nodes, and so that's these equations right here. So I won't repeat any of that, of course. And so now we have all the information we need to be able to write out completely the expression for omega h, the high frequency cutoff, and radiant frequency, and this then is that expression. So all I did was take all of these things, plop them in here, and I use this formula here and multiplied each of these R pi, capital R pi naught resistors, this and this, by their respective C pi capacitors. So this ends up being the result that we get. But what I want to do now that we have this result is take a look at it. And So to look at it and see that in the future, if we have a similar problem, can we save ourselves some time? And that is a very important thing for you to do as you're solving problems like this. And so let's go ahead and do that. Let's take a look at each of these terms and see if any of these terms are very small relative to the other ones. And if they are, then what you should do is neglect them. Okay, so let's take a look at this first term. So this first term is C mu times 1 plus a gain times a resistance here. And so this C mu times 1 plus a gain, that's big. C mu itself is not that big, but the gain usually is. And so because of that, because of this gain here that we get, I guess this gain isn't as big as it could be, but it is fairly large. It's not as big as it could be because we have degeneration, right? In the original circuit, which I'll pull up on the left side, where we have this resistor down here, and that lowers gain as we found before. But it still multiplies that C mu, so that still becomes important. And so depending on what this RS and RB is, if RS is very small, then this becomes insignificant again. But in general, this is going to be a significant term, and because of that, this is a term that I would pay attention to. Okay, so I'm going to use a little bit of this nomenclature here. I'm going to say check means include in our analysis because it's significant. I'm going to do a check bar, almost like an X. That will mean maybe we can neglect this. Like if I'm running out of time, I'm neglecting it. Okay, and then finally if I put an X on it, whether I run out of time or not, I'm neglecting it. Okay, so this first term I put a check there. That means I want to include that term. Just because I've got C mu times some gain that's coming from the Miller capacitance. This term right here, I've got a bunch of capacitors here. This is the term associated with node 3. Okay, and so this thing, I've got a bunch of capacitance there. They may not be gigantic capacitors. There's 2 C mus and a CCS. But this RC1 hanging off here, that's sizable. Right? That's not 100 ohms or so. That's on the order of 5 kilo ohms or 4 kilo ohms or maybe even 8 kilo ohms, something like that. Since that's sizable, this is going to contribute a sizable term, so I'm going to include that too in my analysis. This term right here, this is the capacitance and driving point resistance associated with node 4. I've got CL out there. Usually CL is not the smallest capacitor there. It's a sizable capacitor. I've got a bunch of these things here. So I've got RE2, which is a big resistor. RL, that's whatever our load resistance is. If it's a voltage amplifier, that'll be big. But then I've got this term here, which is R pi 2 plus RC1 divided by beta 2 plus 1. That's not going to be that big. Remember, R pi over beta is 1 over GM. That's about 25 ohms if you have 1 milliamp of current running through the device. RC1, again, could be fairly big. But you divide it by this beta, that's going to shrink too. And so this could be small, meaning that this whole thing could be small. But I'm not going to bank on that because I don't know what CL is generally. So I'm generally going to include this in my analysis. Okay, now this term right here, C pi 1 and this C pi 2. Last time we talked a little bit about these two. We talked about the fact that these are coming from degenerated transistors. And so by a degenerate transistor, what I mean is this type of thing. So I have the transistor, and then I'm hanging a resistor here. Let's take RE2, for example, here in this, which would be this resistor out here. And so if that's it, then my input voltage was here. For this case, which is Q2, for the case of Q2 in our circuit, we're taking our output at the emitter. Right, so that's our V out there. And to complete that picture, that's AC ground. And so what do we have in this? We had a C pi capacitor right here. And this is the capacitor where we're going to ask ourselves, should we worry about that capacitor and what it's doing, or should we just forget about it? And so that specifically will be C pi 2 there. And so we talked about this a bit. We talked about the fact that in this situation, the gain across this, if this voltage here is what I'll call V prime, then since the gain is about 1, that voltage is also going to be V prime. Right? Since I have a gain that's about 1 for that emitter follower. And so because of that, the voltage across this is going to be V prime minus V prime, which is 0 volts. And because I have no voltage across C pi 2, basically I can assume, I can sort of neglect its tau pi 2 contribution. Right? No voltage across C pi 2 means, therefore means I have no C pi 2, as far as I'm concerned. And so if I look at this C pi 2 down here, in general, I'm just going to neglect this. I'm not even going to write that down as part of my solution there, because I know that that's going to be a very small time constant added to this. So I've got one more time constant to look at, and that's C pi 1. So you see C pi 1 on the left side. It's with this transistor here, Q1. But in general, if you're going to try to make a common emitter with emitter degeneration, RE1 is not going to be that big. Because the bigger you make RE1, the less gain you get across here. Whereas for the follower, you don't really care. You want RE2 to be big so that you can get a gain close to 1. In this case, you don't want RE1 to be that big. And so because you don't want RE1 to be that big, this ends up not being so big down here. So this may not completely eliminate C pi 1. That means the gain across this is not necessarily 1. Okay, it's going to be close to 1, but not equal to 1. And so because it's close to 1, in general, I would still ignore this C pi. But you got to be very careful about that. And so I would be careful enough that I'm not going to put an X on that C pi. I'm going to give it that check with a bar down it. Okay? And so this gives you a little bit of insight here. When you're trying to do these types of analyses and you're trying to do them fast, look for these things. If you see emitter degeneration and you have to deal with that C pi 2 or C pi, a capacitor, consider ignoring that C pi capacitor. Definitely ignore it if you're out of time. And just say that the gain across here is 1. And you're just not going to deal with it. But, you know, be on the lookout for these things. Any capacitor you can eliminate saves you a lot of time. So in the end, if I'm doing this analysis, I'm really just looking at these 3 time constants. The one at that node, the one at that node, the one at that node. And I have no capacitors in the end in feedback, which means I really didn't have to memorize anything in the capacitance equations in the inspection analysis handout. So let me bring out that inspection analysis handout. So here's that handout here. You've memorized many of these equations here, and even some of them are not necessary, like this one probably isn't necessary most of the time because it's going to be in parallel with something much smaller. But if I scooch down to the high frequency analysis, you'll notice we have 2 resistors that you had to memorize here. One of them was R mu naught, that you don't have to memorize if you know the Miller effect. And this R pi naught, which we're just saying you don't really have to memorize because the gain from here to here is about 1, which kills off that C pi. And so here, maybe there's nothing to memorize here. So how much do you end up memorizing? I mean, RB, probably you want to commit to memory, or you can figure it out by following the currents, like we talked about before. RE, similar thing, you can figure it out by following the currents, but it's probably better to memorize that. Base to collector gain, all these gains, base to collector, emitter to collector, they have the same equation, except different capital GM values here. And if I have no RE here, this just boils down to GM. So you probably want to remember these. And so you got 1, 2, 3, 4 equations to memorize. Base to emitter gain, if you have a follower, well, that's basically going to be 1. I'm not sure you need to memorize that. And so we've got 4 equations you've got to memorize here, really, that you really need to memorize. The other ones you can just reason out that you can neglect their effects there. So there's not a lot of equations here, so I recommend you memorize them, at least those 4. More would be better, but if you can at least get those 4, then you can do your inspection analysis very, very quickly. And that's how I recommend that you do any large circuit that we talk about. And so now, that's what I want to move on to. Let's move on to some larger circuits. Now, we just designed a multi-transistor circuit. Well, we just analyzed a multi-transistor circuit. Let's now start talking about even bigger circuits and how we make even bigger circuits from there. And so the way to design a bigger circuit is to know your stages, to know what things do. It's a recognition problem. And so remember we looked at this before? Popular amplifier configurations, these building blocks. This is actually a slide that I had shown before, where we identified a couple very often used stages, building blocks. And so this stage here is common collector because the collector is going to ground. And you're taking your input from the base to the emitter. This is what I've been calling an emitter follower. We have a few other common stages here. And so this is a common base amplifier. This is an amplifier where we've, in the small signal sense, right? In the DC sense, it doesn't look like the base is common necessarily, but we make it common in the AC sense by hanging a big capacitor out here to ground, which shorts out the base, and now we get this common base amplifier. And then we've got this common emitter amplifier, or common emitter with degeneration. This is the third stage that we're often working with when we're trying to design or analyze an amplifier. And so your lab number 6 requires design. And if you look at the specs for your lab number 6, it's going to be something that asks for a large input resistance, a small output resistance, and a large amount of gain. You've seen these requirements before. That gets you close to an ideal op-amp. So while lab number 6 is not an op-amp because it doesn't have a differential input, it is an element of an op-amp, and you do run into exactly this kind of design within an op-amp. The only difference is that you don't have a differential first stage. And so how do you go about designing this? How do you go about putting transistors together in stages to guarantee that you've got that large input resistance, small output resistance, and large gain? Well, you sort of put these building blocks together, and I think the best way to talk about these right now is to just tabulate some design guidelines for a multi-stage amplifier. And so here I've got a little table, and I'm going to look at each of our different types of amplifiers that we talked about: common emitter with degeneration, common collector, and common base. And we're going to ask ourselves, what is the input resistance, what's the output resistance, what's the gain, what's the frequency of each of these stages? And specifically, I want to know, is input resistance big or small? Output resistance big or small? Is gain big or small? Is FH big or small? Okay, and when we know this, then we're going to know which stage to use, say, at the front of our amplifier. If we cascade the stages, then at the front we want a stage, if we want high input resistance, we want a stage that has high input resistance. And to get the specs that we want, we have to put the right stages in the right order. And it really becomes that simple. So let's first start with this column here, which we know. We know what we want out of an ideal voltage amplifier. And so I should stress that we're talking about voltage amplifiers in this discussion. When you start talking about current amplifiers or transconductors or these sorts of things, then you want different goals here. But at least for an ideal voltage amplifier, you want your input resistance to be infinite. You want your output resistance to be 0. This is straight out of the ideal op-amp needs. You want your gain to be infinite. And you want your frequency to be infinite. If you can achieve those, you're going to be very, very happy. So let's take a look at the degree to which each of our amplifiers can achieve that. Let's start with the common emitter amplifier, which is really the same as this down here, looking at the left, but without that emitter resistor. So I don't have a drawing of that, so I'm just going to write down here what we're going to expect from this. You've done this, and you've studied this. You've studied this amplifier quite a bit from your Lab 5. And so let's talk about it. What do you think about common emitter gain? Is it large? Is it medium? Is it small? Anyone want to venture a guess? Not a guess, but an answer. Okay, this doesn't work very well, I guess, on remote teaching. So I'll just go ahead and say what you're probably thinking. Now, its gain is not like lab number 6, which is 3,500. But it's not 1 or 5 or something like that. It's a decent amount of gain, like 100, 120, something like that. So I'm going to say for the common emitter that my gain is medium. I'll say that's medium gain. I'm going to use my check slash sort of thing, saying that that's medium. Check means great. Check slash means it's okay. X means no good. Okay, so common emitter output resistance. How close to zero is that output resistance? Well, it's not very close to zero at all, because usually the output resistance is either an R0. Oh, what did I just do? Oh, I said gain. Yeah, you're right. So that is the right answer for the input resistance, by the way, but yeah, I should have put it down in the gain box there. Let's go to input resistance, since I already did it. So the input resistance to a common emitter amplifier is what? Well, I just said it's medium. It's R pi. And so R pi has a value in the order of 2 kilo ohms to 4 kilo ohms or something like that. That's not enormous. Enormous would be 50K, 100K. And so it's not huge, but it's not that small, right? Small would be 100 ohms in that sort, 50 ohms. And so it's medium in that case. How about the output resistance for common emitter? Well, I just talked about that. You're going to have either R0 or RC. Those are resistance on the order of 5 kilo ohms at least. R0 will be 100 kilo ohms. That's nowhere near zero. So the output resistance actually is going to be a large value. And we don't like that, right? Because that's nowhere near zero there. So for the common emitter, the input resistance is okay, the gain is okay, output resistance not very good. And so now the frequency response, it's high frequency cutoff. How about that? Well, with common emitter, that's the classic amplifier that creates the Miller effect. Right? The gain multiplies C mu. It creates a huge capacitor at the input. If you have a capacitor at the output, you also have a pretty good amount of resistance there as well. So the driving point resistance will be big at the output. So either way you slice it, common emitter is not going to do that well as far as frequency response is concerned. So with common emitter, the frequency response is not that great. FH is small, and I'm going to put an X there as well. So common emitter, you've played with it quite a bit in your lab number 5, but it is not the best amplifier out there. How about common emitter with emitter degeneration? So how do we fix some of those issues? And so now I can actually go to the left and start drawing some things in there. And so with emitter degeneration, first of all, I can look at my output resistance. Let's take a look at the output resistance first. And so that output resistance, let me do that in green here. And so that output resistance is going to be equal to 1. It's going to be equal to what? It's going to be equal to RC in parallel with something big, which then is going to be about equal to RC. But RC is still kind of big. Right? So I'm not entirely happy with that. And so it's going to be like the common emitter. If I said the common emitter was too large, then I'm going to say the same thing with common emitter with degeneration. Okay, let's take a look at the gain of this circuit now. So the gain, we know now, is going to be equal to capital GM times the output resistance there, which I know capital GM is GM divided by 1 plus GM times RE. That whole thing then is going to be multiplied by the output resistance, RC. If GMRE is big compared to 1, then I can approximate this thing by RC over RE. Okay, that's not a huge gain. Actually, let me change this right here and give common emitter a bit more respect. It's a relative thing, right? It's not 3,000 like we got for the multi-transistor, but for a single stage, it's pretty good. So let me say that its gain is large. And this is because it's in comparison with the other stages I'm talking about. So let me fix this and say it's large. Common emitter does have a large gain. It's not really medium. But if it has large gain, then common emitter with degeneration is smaller than large, but not too small. So I'll call that medium there. Okay? And input resistance for common emitter with degeneration here. And so what is the equation for that input resistance? Let me go out here. And so that's going to be equal to the RB in parallel with what I see looking into the base of this thing, which is going to be 1 over GM plus RE times beta plus 1, that's going to be a fairly sizable resistance there. Right? So this thing, I'm going to say is big, and so the input resistance for common emitter with degeneration is going to be large. So I would put a check on that as well. Okay, and then finally the frequency response of common emitter with degeneration. It's not going to be as bad as common emitter was, because common emitter had a lot of gain across here. This has less gain, so the Miller effect is going to be smaller. And because I have an emitter resistor here, it's also going to knock out some of the C pi effect there, because I have a gain of nearly 1 from here to here. Okay, so it actually is going to help my frequency response, and so I'm going to consider this frequency response medium there. So common emitter with degeneration is not a bad stage if you look at this. It's got a good input resistance, it's got an okay gain and an okay frequency response, but its output resistance is not very good. Okay, let's move now to common collector. I guess I've got common collector on the previous page here, this page here. So there's my common collector amplifier. Let's just do them in order. So input resistance in the common collector, if I had to write out its equation here, that's going to be that RB in parallel again with 1 over GM plus RE times beta plus 1. For common emitter, for common collector, usually this RE is even bigger than the RE for common emitter with degeneration, and so this is going to be an even bigger amount here, right? This is big, and so I'm going to like this. I have a large resistance there. I'm going to put a check mark there. I like that from common collector. And now it's output resistance. If I had to write the expression for output resistance, I see that RE. That's going to be in parallel with what I see going up through the base, through the emitter. That's going to be 1 over GM plus all this other resistance, RS parallel RB, divided by its beta plus 1. This is all fairly small stuff. So the output resistance, that's small, and I like that. So there's the first amplifier I've got, common collector. Whoop. Whoa. That has the right output resistance for me. The first two that I looked at, I didn't like their output resistances. They were too high. And so common collector's got a lot going for it right now. It's got a large input resistance, which I like, a small output resistance, which I like, but the gain, again, we know what that gain is. It's about equal to 1. That's a very small gain. And for gain, for an ideal voltage amplifier, I don't like that. Now in terms of frequency response, remember the C pi in this circuit actually gets knocked out because the gain is 1. So I can draw my C pi right here and then remove it. Right? It essentially isn't there because I have barely any voltage across it. And so C pi is going to allow me to have a very large frequency response on this because I knock out C pi. I have a little C mu here, but that, it's not amplified by Miller effect. And so it's a fairly small capacitance, and CCS is grounded there. And so in the end, common collector has a very large frequency response range. Okay, so I like that a lot out of common collector. Okay, and so finally common base. Let's take a look at our common base circuit right here. We can do the same sorts of things. We can look at our input resistance for common base. And the input resistance here is effectively equal to RE parallel with 1 over GM. You know that 1 over GM is small. So I could say that the input resistance for a common base is small. Of course, we don't like that for a voltage amplifier. The output resistance in here, that's going to be equal to RC in parallel with something big, which is going to be RC, which in our case, we're still going to consider that fairly large. Okay, so that to me is large because RC is on the order of what, 4K, 5K, something like that. That's fairly large. It's not 0. It's pretty far from 0. So in a relative sense, this is large. So that's no good. So far common base has struck out 2 times as far as voltage amplifiers are concerned. How about the gain of our common base here? And so the gain of our common base is similar to that of a common emitter amplifier. So that gain is like a GM times RC. That's big. Okay, and so if that's big, then I could say large here. And so the common base does well as far as gain is concerned. Now, as far as frequency response is concerned, I've got gain across there. I've got a C pi right here. I've got a C mu right here. These are both shunt capacitors. So none of them are being multiplied by that gain. I don't have a Miller effect type of capacitor. So in fact, common base can give me a fairly large frequency response. So I like common base there. And so what you're seeing here is that of these topologies that people use, none of them are perfect. There is no perfect single transistor amplifier. And so if you're trying to get a more perfect amplifier, you need to put these stages together. And so if I want better performance for a voltage amplifier, for example, if I want performance like what's specified in your lab number 6, I need to cascade some of these stages. And so let's do that. Let's create a better voltage amplifier. So let's do part of your lab 6 right now. So let's just say to get better performance, I'll say better voltage to voltage performance. I have in parentheses up here that I didn't mention yet, but this is for voltage amplifiers here. There's ideal things for current to current amplifiers. You would have different requirements here that you would like, and you would have different circuits that you would use just because of that. But to get better voltage to voltage performance, you want to cascade your amplifiers. Okay, and so for a good voltage amplifier, and this is something that probably you will be doing for your lab 6. I'm doing some of it, but this is not going to be good enough for your lab 6, I'll tell you that right now. I want a large input resistance. And so what gives me a large input resistance? Well, I can choose common emitter with emitter degeneration, or I can choose common collector here. Just looking at this chart here. Common collector will have the much larger input resistance, and your lab wants 100 kilo ohms. That's very large. And so between the two, you probably want to choose common collector there. And so if this is my input, then I'm going to send my input first into an amplifier stage that is common collector. Okay? And so common collector is going to give me a large input resistance. But the gain that I'm going to get out of this is only going to be about 1. And so I'm going to want to follow this with another stage here. And to get my gain, what's reasonable, right? If I want large gain, I've got large and medium from these two. I can also try common base if I wanted to. But if I tried common base, I would have a little bit of difficulty. So let me just draw in the fact. We're going to put another stage here. And the question is, what is that stage going to be? Well, we have to consider a couple things. So remember, as we're getting gain, stage by stage gain, which we did with our multi-stage transistor analysis, I went from this node to that node to get gain. But remember, I had to worry about I had to worry about my resistive loading. And so the output resistance of my common collector I like, because it's small. But if the input resistance of the next stage is also small, then I'm going to get a voltage divider there, a significant voltage division, and I'm going to lose gain there. That's why I don't want to choose a common base. Even though common base gives me a nice large gain, it gives me a small input resistance. And that small input resistance will create a voltage divider with the small output resistance of the common collector, and that will hurt my gain. So I want something that has a reasonably large input resistance. And so common emitter with degeneration would be good, actually. But depending on how much gain I want, if I want more gain than this can give me, then I might choose common emitter because it's got a medium resistance, input resistance. That's probably a good deal bigger than the 25 ohms or whatever coming out of the common collector. And so that's what I'm going to do. I'm going to choose common emitter here. So when I choose that common emitter, this resistance in that direction is going to be what I call medium. The voltage divider is reasonable. Right? I don't lose much gain. Through loading. Okay, and that's something I have to be careful about. So that's why I'm choosing common emitter in this case. The gain in this case is going to be some nice big number that's common emitter. But then out of common emitter, here's where I run into some problems here, because this resistance, the output resistance of my common emitter, that's large. And if I want a good voltage amplifier, I need a small resistance coming out of this. And so my solution to that is to choose an amplifier stage that will give me a much larger resistor here than this resistor there. And out of these stages, who has the largest input resistance was this common emitter with degeneration. We said it was large, but it's not that large. Okay, this common collector, that's what I have to choose. Because common collector uses a larger RE, it gives me a much larger input resistance. And so to make this larger than that, I'm again going to want common collector here. Okay, I know that the common collector is going to give me a 1 times gain across that, but that's okay. I got all my gain from my middle stage there. Here's my output resistance, and the other nice thing about common collector is that my output resistance will be very small for this whole thing. Okay, so we have to worry about input and output resistances and gains, and that's how we're designing this cascade of amplifiers here. So let me be a little more specific about that voltage divider. We're talking about this. Right? Each stage effectively has this. And we have to worry about this gain factor. And we want it to be about equal to 1, which means we want that output resistance, the R0 of the previous stage, to be very small with respect to the next stage Ri. Okay, and so this is the game you'll be playing with your Lab 6. What I just designed here will probably not satisfy Lab 6 because your Lab 6 is pretty demanding, at least in terms of gain. But let me keep going with this in the design. So I'm designing these based on triangles, but when I think of gain, I really want to think of designing this in the small signal sense. So once you've established which stages you want, a good thing to do would be to draw out the circuit, the small signal circuit. So in the small signal sense, we want the following circuit. This is our input voltage. We want to go into a transistor Q1, and this is going to be common collector, so we want the collector to go to ground. We want an emitter resistor RE1, which is a fairly large size RE1. And so this we know is going to give us one of the qualities we like. We're selecting that specifically because for this stage, common collector, we know the input resistance is large. We also know its output resistance is small. And we know that, at least with what we've chosen here, we're going into a common collector or a common emitter stage. So that's Q2. And if it's common emitter, then its small signal circuit should look like this. And then finally, this then drives our output device, which will be Q3. And in small signal sense, we want it to look like this. We want it to have some RE3 resistance here, and then this node finally drives my output. And as we said, the nice thing about this is that the output resistance is small, and this is the stage here that gives us our gain. So we have good gain there, which we know is going to be equal to GM2 times RC2, right? At least the absolute value of that good gain is that. You know it's negative, as we had seen before, right? And so this is the small signal circuit. So this is what you should do, right? Plan out what stages you want, cascade those stages, and draw the small signal circuit. But then now you have to add the biasing for this thing. So in the end, to really design this thing, what decides what the small signal element values are, so what the ultimate gain is of this, is your bias circuit. So we want to add biasing now. And to add biasing, I'm just going to add capacitors now. Well, I'll draw the whole circuit here. So we're going to drive this with some source resistance here. So I'll have some source resistance RS. I'll have my actual source VS here. That's coming to ground. This I'm going to go in through a capacitor, CB1. See how I'm scrunching things in there? I'm doing that because I know this circuit's going to be quite long here. Not that long, but it's going to take up space on my screen. And so for my bias string, same thing as we've always done. I'm going to want an R1 here. I'm going to want an R2 right there, this one going to ground. My R1 I want to go up to a VCC. I want to make sure that's high enough here. So that then becomes my VCC up there. And this now is going to feed my first transistor, Q1, which I want to make into a common collector. So I'm going to take its collector and take it straight up to VCC, because VCC will go to ground in a small signal sense. But I have to bias this up, so I need to stick a resistor right here, RE1. And so this then feeds my next stage, which is going to be a common emitter. Common emitter, which means my collector will have a resistance on it, RC2, there's Q2, but to bias this up, I'm going to need an emitter resistor here, RE2, but to make it common emitter, I'm going to want a bypass capacitor so that at high frequencies or mid-band frequencies, we short out that resistance. Okay, so for this to be common emitter, I want to take my output here. That's what gives me all that gain. So I'll do that, and then I'll go yet into another common collector stage here, which is my Q3. It will have a bias resistor, RE3, which will also determine its input resistance, so I want that RE3 to be sizable. And then to finally go to my load resistance for the next stage that we're driving, I'm going to want a capacitor here as well, which I'll call CE3. Okay, and that is my circuit then. This is the circuit that gives me good input resistance, good output resistance, and good gain. I will say it does not have enough gain for your lab number 6. So for lab number 6, you will probably have to add another stage. That's why we give you 4 transistors in lab number 6. For now, though, let's take a look at this biasing. So I've drawn up this circuit here. Let's now write out the equations for biasing in this. And so this is something that you should be able to do very easily now because you've done it several times and you've done your lab number 5. Except in this case you have some differences in that you have several transistors there. So biasing for stability, as usual, you want I bias to be greater than 10 times IB1. I bias I've been calling this current sort of going through R1 and R2. Right, that's what I call the I bias current. But then you could ask the question, well, what about the I bias current for the rest of the stages? You want these stages to be similar to that as well. Okay, And so what you really want, if I were to look at this, is you want the current from the previous stage, so I previous, to be greater than 10 times the base current of the next stage. Okay, so in this first thing, I can call this current to previous, and this current going in here is my IB next. So you basically just want to make sure that the previous current, collector current here, is a good deal bigger than the base current going into the next stage. That's going to be easy for a lot of your stages, but maybe for your last stage it might not be if you have to get that output resistance very low. So these are things you do have to watch for there. Okay, but this is for good stability. This is how you want to design, and then the rest of this analysis is like we've done before. And so I can identify this as a VB1. This is IB1 there, and I can immediately write that VB1, if I ignore IB1, is going to be VCC times R2 over R1 plus R2. Okay, and so this assumes this neglects the IB1 for that, which you can do if you have good biasing going on, if you're following these rules that we had up there. This then creates, of course, the voltage at the emitter of Q1, which is just going to be that VB1 voltage value that we have minus a forward active on voltage of a transistor, which is VBE on. Right? And once we have VE1, we can get the collector current of device 1, which is what we want. We're basically saying that that collector current is about equal to the emitter current, and the emitter current is just VE1 divided by RE1. And we can keep going with this to the next stage. We know what VE2 has to be equal. That has to be equal to VE1 because, right, if this is VE1 right here, then to get to VE2, we have to drop another VBE on. So that says that VE2 is simply equal to, is simply equal to VB1. We can go all the way back to the starting point here, where VB1 is right there, minus 2 times VBE on. Okay, so we have that equation for VE2, and as soon as we know VE2, of course, we now know IC2. That's going to be about equal to IE2, which is going to be VE2 divided by RE2. Okay, and so we can continue with this here. That is going to create the current going through Q2, and so I now know IC2. And so I can take that IC2 and I can determine what the collector voltage is right here, VC2, which is then going to be equal to VB2, and it's going to allow me to get VE2. Sorry, VE3, VB3 and VE3. And that VE3 is then going to allow me to get the collector current through device 3. So just to complete this analysis, this gives me VC2, which is going to be VCC minus that IC2 times the RC2 that I have, and then the VE3 is going to be equal to VB2 minus a VBE on, and from that VE3 finally I'm going to get IC3, which again is going to be about equal to IE3, which is going to be equal to the VE3 that we just got divided by RE3. So what you're noticing is that all these collector currents, they're basically just VEs divided by whatever the emitter resistor is. So the emitter resistor becomes very important in setting the bias point of this. The emitter resistor, as I think you found in Lab 5, is also very important in setting the output swing of this circuit here. And so the output swing in Lab 6 has got a certain spec for output swing. And so let's take a look at what that output swing is going to do. Let's go from this V out here. And let me go to the next page here and think a little bit about what that output swing means and whether that large output swing, remember that output swing is going to be fairly large in this case. Let me go blue here. So we want to know whether that large output swing means that we're no longer in the small signal domain. Right, so we should ask that question. All of our analyses, remember, our ability to handle these nonlinear circuits, and that's what we're really doing, right? It's easy to forget that's what we're really doing because we made it so simple with small signal analysis. But remember, the small signal analysis only works when the voltages that we're using are very small. And so specifically, if I have this large output swing here, and I can draw what it looks like as a function of time, and so this is going to be my output voltage there. I'll put that slash down there to say that this is, well, I won't put that, I don't need to put that slash there. Well, I will. It's the total signal basically, but even the small signal looks the same in this circuit here. But this is going to be some sinusoid, and hopefully it's not clipping, but it is a big sinusoid here. So this is going to be whatever V output max is here. And this can be volts. It's not millivolts, right? So for example, 2 volts could even be 10 volts, depending on your circuit there. And so if it's that big, then you can ask the question, does this violate our small signal design criterion? And remember what that criterion was. That criterion was that you need to keep your small signal VBE much less than the thermal voltage, which is 25 millivolts. Okay? And so we're seeing an output voltage here that's a lot bigger than 25 millivolts. Are we violating our small signal condition? Well, only if VBE is that big. And so let's take a closer look at that Q3 right here. And so that Q3 is this. So if I draw it bigger here, then I effectively have something that looks like this. That's Q3. It's got a resistor RE3 here. And I have an input voltage and an output voltage for this stage. And for this, what can I say about the voltage dropped across VBE? So one thing I can say is that the voltage dropped, VI is a pretty big voltage here, and V out is a pretty big voltage. So if I wanted to draw VI here, then VI is going to look something like this. It's going to be that sinusoid that I just drew up there. Okay, and so let's say that VI is 1 volt, clearly bigger than 25 millivolts right there. Okay, so the question is, are we violating our small signal issue, our small signal criterion here? But first, let's plot out our V naught. So what's V naught going to be for this particular stage? Well, this is a common collector stage. Right, so if it's common collector, then V naught is going to look just like I naught, right? The gain is 1. The gain is not going to be exactly 1. Maybe the gain is 0.99. Right? So say that the gain across this here is not going to be exactly 1. And so if the gain is 0.99, then this voltage here is 0.99 volts across that. And so we can now do this analysis, actually. We could say that the voltage that I see, let me go to a different color so it doesn't get too cluttered here. But the voltage that I see from here to ground, right, that's what I can call my VI voltage. That's this voltage up here. That's what I see from there to ground. But the voltage I see from here to ground, that's my V out voltage. That's this. Okay, that means that at any given time, I'm dropping across here, since this is 0.99 volts. I'm dropping 0.99 volts across here, which means what I'm dropping across here is 0.01 volts. That's VBE. 0.1 volts. That's 10 millivolts. That's less than 25 millivolts, which means it's less than our thermal voltage. So we do satisfy our small signal requirement. So you see how that's happening. That's happening because even though we're putting a large input resistance into this circuit, most of it's being dropped across this resistor. Very little is being dropped across the actual VBE of the transistor. And these are all small signals, right? That's a small signal voltage. This is a small signal voltage I'm talking about, right? But most of it is being dropped across this resistor, very little across VBE. VBE stays 10 millivolts, lower than 25 millivolts, so we continue to satisfy our small signal criterion. That's what's going on there. So all of our analyses, even though we've got such a large voltage going to the output, all of our analyses are still correct as we're doing all of this. Okay, so with that, you have a lot. You can start your lab number 6 even over the weekend if you want to do that. And I recommend starting as soon as you can. I would recommend doing that because what have you got coming up? You've got next week, you have a lecture on Monday, there's no lecture on Wednesday. And so you'll be off on Thanksgiving. And then coming back, you're going to have at least a SPICE file checkpoint. That's not going to be difficult. You just have to create something like this, maybe with 4 transistors and make sure it biases up, and you can almost guarantee it'll make 2 of the specs. It might not make the gain spec or the input resistance, but it'll probably make the swing spec or something like that. But that's what you need for your checkpoint on Monday after we get back from Thanksgiving. So I would try to do some of this analysis now. That's why I wanted to do this part of the lecture now before getting into MOS inspection analysis. So any questions about what I just did here? All right, well, we're out of time. So have a nice weekend, and I will see you on Monday.